So let's take a look at a representative algorithmic decomposition of an expression tree. A typical way of doing this would implement the expression tree using some kind of C-like structure and union to present the main data structure. So we might have, as we show here, some kind of tree node struct which contains a number of different parts. One thing we'll have here would be a type tag which is going to be used to indicate what kind of tree node we've got. Do we have a number node, a unary node, a binary node, or whatnot? And this is represented as some kind of enumerated type, or enum. We'd also perhaps have some kind of reference count, which we might use in order to be able to share various parts of these nodes if you have common subexpressions. We'd also find some way to represent the actual value of the node. If it turns out to be a number node, the value would be an integer of some kind. If it's some kind of unary or binary node, then the value might be a plus or a minus or a multiplication symbol that could be used to indicate what kind of node it is. And then the last set of things we'd probably put in an expression tree node using an algorithmic decomposition would be something involving the children, whether it's got one child or two children or no children. And so for all this, we use things like unions, which are trying to save some space in certain cases by having the offsets of all the structure begin at the same place, at 0. If you take a look at this and you were to actually graph the way that the memory was laid out, you'd see an object that looks something like this. Every instance of tree node is going to have the enumerated type, reference count, the value, and then one or two recursive pointers to the various tree nodes for the children. If we were to try to graph this using some kind of UML-like notation, the output might look a little bit like what's shown on the screen. Another thing that would happen if we typically used an algorithmic decomposition is we'd end up with some kind of function to build and evaluate the tree. We're showing here an example of a function that is used to print the contents of the tree. And as you can see here, it's passed in a pointer to the root of the tree and an output file to output the result. And it starts by first switching on the type tag, which is that enumerated type we looked at before. And depending on what kind of tag it is, then different cases will occur using a switch statement. So if it's a number, we'll go ahead and print out the number. If it's a unary node, then we'll go ahead and first print out the unary operation, and then we'll recursively make a call to traverse down to print out the subtree that's part of the unary operator. If it happens to be a binary node, once again, we'll do some recursion. We'll go down the left-hand side of the tree first. When we come back up, we'll print out the operator, and then we'll recurse down the right-hand side of the tree. And all these various operations will take place using the tree node data structure, looking inside the various fields in order to direct the way in which the function progresses.